I want you to picture a document I came across. It's heavy.
Metaphorically heavy.
Right, though the PDF file size is probably pretty big too. It's a proposal, a roadmap, and the title is something else. A civilization-grade design engine. And, usually when I see a phrase like that, my whole Silicon Valley buzzword alarm just starts blaring.
It does have a certain dramatic flair, doesn't it?
It really does.
Yeah.
But then I started to dig into the actual content. We are not talking about, the next Photoshop update or a slightly better AutoCAD.
No.
This is a detailed technical and financial breakdown of a 10-year, $1 billion plan. A plan to fundamentally rebuild how we engineer physical things.
Look at the hook they use. The metric for success is just wild.
The 12-year-old test.
Exactly.
The proposal literally claims that if they build this system correctly, a 12-year-old could sit down and in maybe 1 or 2 hours design a fully flyable, safe, manufacturable aircraft. I mean, not a drawing of a plane, a real physics-compliant machine.
And that's the core tension of this whole document, right? On one hand, it sounds like pure science fiction.
Completely.
But on the other, the authors argue, and pretty convincingly, I think, that this is structurally inevitable.
Structurally inevitable. That is a bold, bold claim. So for today's deep dive, that's what we're going to do. We're going to tear this proposal apart.
Let's do it.
We'll look at the tech stack, the billion-dollar budget, and really ask, is this actually possible? Or is it just a very expensive fantasy?
I'm ready. And I think to understand why it's such a big deal, we have to start with the problem itself. Because people assume we already have this.
Right. We have CAD, we have 3D printers.
We have all these tools, but are they intelligent? That's the question.
That's what I thought at first. I mean, engineers use CAD every single day. SolidWorks, PID.
Fusion 360, yeah.
But the source material makes this distinction that I think is so crucial. It calls current CAD tools fancy digital drafting boards.
It's a harsh assessment, but it's not wrong. I mean, think about what CAD actually is, computer-aided design.
Right.
But it's really computer-aided drawing. When you draw a circle, the computer just sees a circle, a radius, a center point.
It doesn't know it's a wheel.
It has no idea it's a wheel. It doesn't know it's supposed to support a 2-ton truck. All the physics, all the intent is in your head.
The human is the one doing the real engineering.
Precisely.
Okay.
And that creates this horribly fragmented workflow. We call it the over-the-wall problem.
Okay.
You, the designer, you draw the shape. Then you throw it over the wall to the simulation engineer, the PhD.
Who runs it on a supercomputer for 3 days.
And then they find out the wing snaps off and they throw it back. And you change it and throw it back.
And that loop takes weeks.
Months. Sometimes months. And then, once you finally get a design that works in theory, you throw it over another wall to the manufacturing engineer.
I mean, look at it and say,
we can't actually build this.
so you start all over again.
Right. So this proposal, this design intelligence system, its whole purpose is to just burn those walls to the ground.
To unify them.
Exactly. The goal is to move from CAD with AI plugins to a truly AI-first engineering system, to compress that entire timeline design, simulation manufacturing into a single real-time loop.
Let's go back to that 12-year-old.
Yes.
Because that's what helps me visualize what AI first really means. If I'm that kid, I am definitely not calculating Reynolds numbers.
Yeah.
Or drag coefficients. So what am I actually doing?
You are providing intent. That is the key word in this whole document. The user inputs high-level requirements.
Like?
I want a drone. It needs to carry a GoPro. It needs to fly for 30 minutes. It must launch from a grassy field. Simple stuff.
And the AI just takes it from there. Because that sounds a little bit like those image generators.
I was thinking the same thing.
You type plane, and it gives you a cool-looking picture of a plane with 3 wings and a melting propeller. It looks neat, but it defies physics.
And that is the absolute crucial difference here. This isn't a diffusion model just trained on pictures of planes. It's an engineering engine.
So it knows physics.
When the AI generates the geometry, it's not just guessing a shape that looks right. It is simultaneously calculating the aerodynamics for stability. It's sizing the spars inside the wings to handle the structural loads.
So it's optimizing for physics in the background as it's drawing.
In real time.
Yeah.
And the final output isn't a picture, a JPEG. It's a full manufacturing package. The source says it outputs the CNC tool paths to cut the metal, the bill of materials to buy the motors, the assembly instructions.
It hands you a kit.
It literally hands you a kit.
Okay, that is a massive, massive leap. You're basically automating the work of 3 different engineering disciplines.
Yeah.
So the source breaks this down into 4 subsystems to make it happen. Let's walk through them because I really want to see if the tech actually holds up.
Let's do it. Subsystem 1.
The AI-driven parametric modeling engine. They call this the kernel, the brain. So why do we need a new one? Why not just plug AI into what we already have?
So this is where we get a little into the weeds of B-rep versus implicit geometry. Boundary representation. It's how basically all current CAD works. It defines an object by its edges and surfaces. The problem is, it's incredibly fragile. Ever hear of the topological naming problem?
Sounds like a migraine.
It is the absolute bane of every mechanical engineer's existence.
Right.
So say you design a block, you drill a hole and then you round the edges of that hole. That's a fillet.
Okay.
Now you go back and change the size of the block. Suddenly the internal ID for that hole changes. The fillet loses its reference and the whole model just breaks.
So modern CAD is brittle.
Extremely. And you can't train an AI on something that brittle. The AI would spend all its time just fixing broken geometry. This proposal suggests using something totally different. Neural implicit surfaces and graph neural networks.
In English.
It means the system understands the logic of the part, not just its surface. It gets design intent. So if the AI decides the fuselage needs to be longer to fit a bigger battery, it knows, okay, that means I need to move the tail back and I have to thicken the rear connectors. It regenerates the model robustly without a cascade of error messages.
So that's step 1, a robust, flexible geometry engine. But a shape is just a shape until you add physics.
Exactly. Which brings us to subsystem 2, the simulation engine.
This is the CFD FEA for every one layer.
Right, and we use these acronyms a lot. Let's just quickly define them.
Good idea, CFD.
Computational fluid dynamics, simulating airflow, water flow, that kind of thing.
And FEA.
Finite element analysis, that's for stress. Breaking apart into millions of tiny little pieces to see where it will bend or snap.
Okay, so the source claims this system can run these simulations in real time. But like we just said, these usually take supercomputers hours or days. How do you cheat the physics?
You don't cheat physics, you learn it. They propose using what are called surrogate models.
Surrogate models, explain that.
Okay, think of it like a chess game. A standard computer plays chess by brute force. It calculates every possible move 10 steps ahead. That's your traditional simulation. Massive compute power.
Right, and a surrogate model is?
A surrogate model is like a chess grandmaster. The grandmaster doesn't calculate every single move. They look at the board and they just intuit the right move based on patterns from thousands of games.
So the AI has seen the physics simulations so many times, it can predict the outcome.
Exactly. Using things called physics-informed neural networks, or PNNs, it can predict the result with, say, 99% accuracy, but in milliseconds. It recognizes the pattern of airflow over a wing instead of calculating every single air molecule.
And that speed changes everything.
Everything. The source gives this example where you're dragging a slider to change the wing's angle, and a little notification just pops up instantly. Warning, wing stalls at 14 degrees.
Or suggestion, sweep the wing back 5 degrees to reduce drag by 12%.
Yes. It's like having a live wind tunnel running inside your monitor. Simulation becomes a design tool at the beginning, not a verification step at the end.
That is a fundamental shift. But there's a huge risk here. If you give a 12-year-old, or let's be honest, me, a tool this powerful, I'm going to design a death trap.
Or a drone that flies straight into a crowd.
Right. Which brings us to subsystem 3, the AI-driven design tutor. This is the safety net.
It's way more than a safety net. The document describes it as an active educational layer.
So it's built on large language models, LLMs, like we see everywhere.
Yes, but these are heavily fine-tuned on engineering textbooks, on FAA safety standards, on physics principles. It's not just a chatbot.
So it's not going to be like Clippy popping up saying, it looks like you're building a plane that won't fly.
No, it explains why. If our user puts the wings too far back on the fuselage, the system doesn't just say no.
What does it do?
It highlights the problem and says, this design is unstable because the center of gravity is behind the center of lift. Here are 2 ways to fix it. Try moving the battery forward or shifting the wings forward.
Wow. It turns the software into a mentor.
That's the key. It democratizes the knowledge, not just the tool. It prevents you from making something dangerous by teaching you the principles in real time.
Okay, and finally, subsystem 4 is the infrastructure. Cloud compute and collaboration. This seems pretty straightforward.
It is, but it's essential. Those surrogate models are fast, but for the final stamp of approval before you actually manufacture, you still want to run that one heavy brute force simulation.
To be absolutely sure.
And the system just offloads that to the cloud so your laptop doesn't melt.
Okay, so we have a brain that draws, a heart that simulates physics, a tutor that keeps you safe, and a cloud backbone. It sounds incredible, also sounds incredibly expensive.
Extremely.
And the proposal puts a number on it, $1 billion over 10 years. And they call this a quantized and adversarial estimate.
Which is a very fancy way of saying they actually did the math and tried to prove it couldn't be done, but landed on it could.
Let's look at that budget,
Yeah.
because $1 billion is a lot of money.
Yeah.
The biggest line item is the core kernel, $350 million. That seems really high for just the code.
It does, until you look at who you need to hire. To build a new geometric kernel from scratch that can do all this, you need the world's best mathematicians, the best computer scientists.
Right.
The source estimates a team of 120 elite engineers working for a decade. You're poaching these people from Google, from NVIDIA, from Lockheed Martin. That gets very expensive, very fast.
Then you have $150 million for the AI modeling engine, $200 million for the simulation team. And here's one that really caught my eye, universal import. For $80 million?
Yeah.
Why spend almost $100 million just to open old files?
Because legacy data is the biggest moat in this entire industry. If your brand new system can't read the files Boeing made in Satia in 1995, Boeing will never, ever use it.
And reading it isn't simple.
It's an AI challenge in itself. The system has to take a dumb 3D shape from an old program and reverse engineer the logic, figure out how it was built.
So that $80 million is the cost of building a bridge from the old world to the new one.
Precisely.
Now, $1 billion is a big number, but playing devil's advocate here, in the grand scheme of things, is it really?
I was thinking the same thing. What's the development cost of a single new car model? It's easily over $1 billion.
The F-35 fighter jet program was what, $400 billion?
Something like that, yeah.
So for the price of developing one mid-size sedan, this proposal claims we could build an engine to let anyone design anything.
When you put it in that context, it almost sounds like a bargain. And the source argues this is the upper bound cost. The price to not just compete, but to make every other tool obsolete.
Okay, but this brings us to the trillion-dollar question. Why now? Why didn't Siemens or Dassault build this 5 years ago? Why isn't Google all over this?
Convergence. The source material is very clear about this. 5 years ago, this was physically impossible. The pieces weren't there.
What was missing?
The hardware and the math, basically. First, GPUs. The explosion of compute power from gaming, then crypto, and now the AI boom. We finally have the raw horsepower.
Okay, the hardware's there. What about the math?
Neural CFD, using AI to simulate fluids. That's bleeding edge. We're talking about research papers published in 2021, 2022, and things like NERFs, neural radiance fields, which let computers understand 3D space from 2D images. That tech is just maturing right now.
So the argument is we've moved from an invention problem to an integration problem.
That's it, exactly. All the pieces are finally on the table. Someone just needs to assemble them. It's no longer a research fantasy. It's an engineering project.
A very hard, very expensive engineering project.
But a tractable one.
You know, we've spent a lot of time on this 12-year-old designing a plane image. It's a great hook. But as we wrap up, I want to pivot a bit, because the implications of this go so far beyond just a cool hobby.
Oh, absolutely. The 12-year-old is just a proxy for any non-expert.
Exactly. Think about a biologist in a rainforest. She needs a very specific type of drone to track a very specific animal. She knows what the drone needs to do.
But she doesn't know aerodynamics or structural engineering.
So today, she's stuck. She either hacks something together off the shelf that doesn't quite work, or she has to hire an engineering firm for 50 grand.
With this system, she just inputs the mission parameters. Fly for this long, carry this sensor, land on that branch. The AI handles the lift-to-drag ratios. She gets a custom tool that solves her exact problem.
It decouples innovation from engineering expertise.
That is the profound shift. Right now, to invent a physical machine, you really need to be an engineer. This system says, no, you just need to have the idea. The system provides the engineering degree.
It's the democratization of the physical world. We saw it with writing, right? The internet let anyone be a publisher.
We saw it with photography. This is for stuff.
And remember, the output is a manufacturing package. It connects the digital idea directly to the factory floor. The barrier to entry for building complex hardware could drop to almost zero.
Which is both incredibly exciting and a little bit terrifying.
As all civilization-grade shifts are.
True.
The source ends the proposal with detailed staffing plans. modular architectures. It's clear that whoever wrote this is ready to start building tomorrow.
The roadmap is there, the tech is ripe. The only missing variables are the capital and the will to execute.
It makes you wonder who would pick this up. A government. A tech giant.
Or a startup that's just crazy enough to try. Whoever gets there first basically controls the operating system for the physical world for the next century.
$1 billion gamble for $1 trillion prize.
I think I'd take those odds.
Me too. And I want to leave our listener with a final thought. We've talked a lot about the tech, the budget, the planes, but turn this back on yourself.
The listener.
Yes, you listening right now. Forget the airplane for a second. If this system existed today, if you had a super engineer in your pocket that could handle all the physics and all the safety constraints, what would you build? What problem have you looked at in your daily life and just thought, if only I could build a little machine to fix that? But you stopped because you didn't know how.
Because if this proposal is right, not knowing how is about to become an obsolete excuse.
And the only limit left will be your imagination. Thanks for taking this deep dive with us.
Catch you on the next one.